The purpose of this presentation is to demonstrate how to perform a multiple regression on SPSS. We have uploaded the assignment data set into SPSS and we have it here in front of us. The first thing that I would always do is inspect the data visually, and in this case I can see that I have 4 variables, and these 4 variables are divided into one outcome variable or a dependent variable, which is salary, because we are trying to predict salary by a certain set of independent variables or predictor variables. Those independent variables are age, years of experience, and in this case, beauty. Now, as I'm doing the visual inspection of the data, I can already tell that maybe I'm going to have a problem here. Why? Because as age increases, so does years of experience. And so one of the objectives of regression is to be able to account for unique variance of each one of the variables. So conceptually, I can already see that I might have an issue here between these two variables. The first thing that I would do is, and this is a practice that is not a requirement in multiple regression, but it's still a pretty good practice, would be to conduct a simple bivariate correlation to see how these variables behave together. And so in this case, what I see is that the variable salary, which is the outcome variable, of course, with salary is correlated perfectly. That would make sense. With age, or years of, actually this is age. Let me see if I can put a little bit of color on this. Okay, that's too much of a job, so I won't. 0.39. Number of years as a model, or experience as I refer to it, 0.33. We can already see that these are very similar in terms of the relationship that they have with salary. This is the R coefficient, correlational coefficient. And attractiveness, as you can see, is not related at all. If 0 is absence of shared variance or correlation, at 0.06, we're very close to 0. Where the problem lies, however, is when I look at age and I correlate age with number of years as a supermodel. I am now almost at 1, which is a perfect correlation. And so, again, if conceptually I thought that there was a problem, now I'm starting to confirm that problem by looking at the correlation coefficient with the shared variance of these variables, almost 1. And so, as I see this, I can anticipate that I'm going to have a problem of what is referred to in regression as multicollinearity, where variables are highly correlated, introduced into a model, and unique variance cannot be accounted for by the model. Now, the important thing about regression, or about statistics in general, is that you as an individual builds the model. You build a model on sound principles and practices. Once I've run those correlations, I am going to actually test this model as it's recommended in the book. Regression, and of course, we would do all the descriptive and make sure that we check for linearity and so forth, but we're not going to do that for the purposes of this video. We conduct a linear multiple regression. The outcome variable, or the dependent variable, is salary per day, and these are the independent variables. If I click on statistics, I can ask for collinearity diagnostics. We can also ask for a Durbin-Watson, which will help us determine whether the errors are not correlated. This is also referred to as autocorrelation. Click on continue, and if you wish to, you can ask for some plots. Usually the typical plot that we look for in regression is the Z, or standardized predicted by the standardized residual. And we'll click on continue here, and then we wish to save a few of these distances to examine influential cases. I know how to interpret Cook's distance. I know how to interpret, actually we can interpret all of these with the proper aid of rules of thumb, or with the proper aid of instructions that is available to you in your textbook. But I just don't want to click on a whole bunch of stuff, as many of us do when we're working on this, and then just have a lot of output that I struggle with understanding. So residuals is something that we can look at, and standardized residuals are a good idea. So I have Cook's distance. We could actually click on Mahalanovi's distance as well, and examine influential cases from that perspective. But I think that with Cook's distance we're okay. We can click on continue, and there's actually very little extra that we're going to click on here. And let's go ahead and click on OK. So this is the output that we get. The first box tells it that we ran a regression with salary as an outcome variable, and that we included attractiveness, number of years as a supermodel, or experience and age as predictor variables or as independent variables. This is our R coefficient. This is our R square, which tells us what percentage of the variance is accounted for by this model, and we usually consider this or interpret this as a percentage, and so this would be looked at it as 18% of the variance accounted for by this model. An adjusted R square change, actually not change, but the difference between adjusted R square and R square allows us to determine the goodness of fit of this model. We're looking at autocorrelation now through the Durbin-Watson test, and the rule of thumb is 2 is ideal. Deviations away from larger than 3 or smaller than 1 should be considered as problematic, and so we would have to examine our data. The variables that have been included might be autocorrelated. The errors actually of those variables. The next box that we look at is at the ANOVA box. We may be interested in looking at the significance of this model, and we do find it to be significance, the F ratio. And of course, if you understand this, this is the regression or variance accounted for, this is the unaccounted for variance, and this is the total. So this plus this is this. If you take this value, the sum of the squares of the regression, and you divide it by 3, you will end up with the mean squares value. So 10,871 divided by 3 is this number here, 48,202 divided by 227 is this value here. This divided by this actually gives you the F ratio, and this F ratio, 17.06, is significant. So the next thing that we would do is, after we confirm that we have a significant model, is we will look at our coefficients box. Now, the first thing that I am attracted to is to look at the collinearity diagnostics or statistics, and I do see that based on a rule of thumb of 10 and above being problematic, and we do find that these two variables are above here, that value of 10 at about 12 and a little bit, and 12 and a half here. And so automatically I understand or recognize that there's a problem of collinearity. There's also a separate collinearity diagnostics here, and just very quickly looking at this, values above 30 are problematic on a rule of thumbs type of decision making, and we do have values that are above 30 in this case. So am I going to look at anything else? I could start looking at my standardized residuals. I can look at the Mahalanovi's distance, Cook's distance, and so forth, and attempt to determine if there are problematic or influential cases in this model. And as I look through this quickly, I don't see any. If I look at the standardized residual plot here, I can see that I do have a little bit of a pattern. I usually don't want to see this pattern. I can also see that I have some values that are way above 2 standard deviations, and that actually occurs in both directions. But again, I'm not necessarily going to do anything about that. That's not necessarily our biggest concern today. Our biggest concern is now that we have issue of multicollinearity. So because this is not our research, actually when you ask for standardized residuals and Cook's distance and you wish to examine these individually, you can do so here. So if I was looking for values that are larger than 1 for the Cook's distance, I could actually sort these descending, so I'd have the largest value at the top. And I see that I don't necessarily, or actually this right here could be a problematic case. And yes, this one has emerged as problematic. At 95, you know that this supermodel is making quite a bit of money compared to everybody else. These right here are my standard residuals, standardized residuals, and we can see that at 4, these are quite a bit away from the mean of 0, and they could also be considered problematic or influential. So maybe in a perfect world we would eliminate these 2 cases as influential, or run 2 separate regression models, one with them included, one with them excluded, and then compare the models. But anyway, in this case, what I'm going to do is I'm simply going to run 2 separate regression models, one with age, one with years of experience, because we recognize that we have an issue of multicollinearity with them. And so this is what ideally your final assignment would look like. Let's remove number of years of experience, and we already have everything that we have or that we wish to have clicked, so let's go ahead and just run that model. And now we can see that the R has actually dropped a little bit. Our R square has also dropped a little bit from 18 and a little bit to about 15 and a little bit. So 15%, about 60% of the variance is accounted for by this model. The adjusted R square is 0.15. Difference between these 2 numbers probably reduced a little bit now. The Durbin-Watson has dropped. Our collinearity has actually been fixed. We don't, since we have only attractiveness now in this model, and we have the issue of, or the variable of age, we see that those originally were not necessarily highly correlated, and now as we run them together, our collinearity issue has disappeared. We have values less than 30 on our collinearity diagnostics for the condition index, and we can be pretty satisfied with the fact that this model is not necessarily struggling with collinearity issues as it was before. We still have relatively the same values because no changes have been made, except that we have eliminated one of the variables in terms of residual statistics. We still see that pattern here. We still see some of these outlying cases which could be considered influential. So let's go ahead and run 1 second model, and in this case I'm going to pull out age and bring back in number of years, and I'll click on OK. So as we run this, we can see that 33%, actually 11% of the variance is accounted for by this model, and our adjusted R square is 0.10 or 10%. Still a significant model. We don't have any issues with collinearity in this case as well. If we were to interpret this, and we could have done the same thing with the previous model, we would be looking at what the effect of number of years of experience is on salary. Now, this is a negative value, suggesting that when everything is 0 in this model, supermodel salary is negative $6 a day. Now, the concern with that is that conceptually that really doesn't make any sense. It's probably a good idea to mean center these variables, and I'm going to show you how to do that in just a second. So we can still see some of the same behaviors occurring over here. So we might have some of these influential cases here. This might be the $95 and $89 a day supermodels. We might think about eliminating those. We see that our Durbin-Watson is actually in a little bit of trouble here. What I would do in a final model is probably run, because I know that attractiveness is not a significant predictor of salary, I would eliminate salary from the model and simply run regression with number of years of experience as a supermodel. And as I click that, I've gotten rid of that. Now I probably have the best measure of what the effect of the years of experience has on the supermodel salary on a daily basis. So I talked about mean centering just a second ago. I'm going to go ahead and do that because it's important to, if we wish to interpret these coefficients properly, if we mean center this, it would make a lot more sense. So the first thing that I'm going to do is simply describe, because I want to get the means for these two variables, age and number of years of experience. Those are the two variables that I'm going to mean center. So the means are 18.06 and 4.58. I'm going to write. So what I'm going to do now is I'm going to transform that in just a second, and I'm going to call the first one 06 and underscore mean center. I'm going to bring in age and simply say minus 18.06. I'm going to click on OK, and I'm going to transform my other variable, or create a new mean center variable for experience. And I'm going to delete this, and I'm going to bring in number of years as a supermodel minus 4.58. And click on OK. As I do that, now I can see that if I were to describe these two variables, let's get rid of these and let's bring in mean centered age and experience and click on OK. Now we see that the mean is actually 0. There's a little bit of change there because I didn't use all the numbers in the in what the actual mean of the two previous variables was. I simply used the first two numbers, so, or points after decimals after the point. So the story is that now my mean is 0. If I were to run this regression model with the new experience or age as a supermodel or years as a supermodel, click on OK. I get the same model, same values for anything, but when I interpret my coefficients, if everything is 0 or nothing is counted for in this model, the average daily, on average, supermodel will be making about $11.32 a day. 1 year of extra experience of the supermodel will increase the salary by 3.42. So if you have a supermodel with 2 years of experience, you can multiply this number times 2, add it to this value here. Let's go. Yeah, this is much more interpretable than the previous one where you had a negative constant. If we scroll up a little bit, we can see that we had previously a negative constant here. So we're interpreting this
so I ran two separate
with
models
negative values, and that is problematic. Not necessarily, it's just an extra constant in mathematics salary, but again, it's 11. You can still figure out from which matches with what in this case. When the value is mean centered, 11.32, but again, we rounded off with a mean centering process. So when everything is 0, the average salary for a supermodel is 11.31. 1 extra year in terms of age affects the model by 2.63. So the salary will increase by 2.63. So if